get started. I'm going to do a couple more of these hypothesis testing. I did actually collect some data that we can use. And then the second one I'm going to do is just a made up one because I couldn't find good data on the other one. In this story, the background between this story is that they're doing I think you would call it, although I can't remember the correct term, you're going to do a safety check on a medication. So one of the things that the FDA do when a new medication is up to be used, even the COVID-19, which was a fast track one, they still did some of this as well, is that you test for side effects and for bad side effects. And so this particular drug that that I got the data from, they were testing that it would be reducing the blood pressure. Now, that's not what its job was, right? It was actually an anti-inflammatory drug, right? It's meant to reduce swelling and things. But they were worried that this drug might be causing a reduction in blood pressure. And so 115 is a kind of the average that they were using for the systolic blood pressure. So that is the normal kind of value that they were looking at. And they did a large sample of people. Do you know that they normally use students? Because students will do anything for money. And very often they use medical students as well. So they just go to universities and say, we need, 100 volunteers from here and 20 volunteers from there. And they got a whole bunch of students, essentially. And they paid them money and they gave them the anti-inflammatory drug. And all they were doing it for was to test the effect on the blood pressure, right? And so this is the results they got. The blood pressure on this group was 114.5. So it did reduce the blood pressure. And the standard deviation was 5. And evidently there's a thing called I can't even say the word. Is it cytolic? Pronounce that word for me.
Systolic.
Systolic blood pressure. Is that the one where it's going into the heart or out of the heart? I think that's something to do with it, isn't it? Right. There's two numbers. There's another one as well, but that's the one that we're doing the data on. And so what we were going to do now is we're going to check this out and see whether or not this drug is having a significant reduction, right? Statistically significant, I should say, on the blood pressure. Well, let's get the standard error. S over square root of n. That's actually a very, very large sample. Normally when they do these things, they do them with reasonably small samples. And then if they think something bad's happening, then they spend big money on this one. So maybe they did find some results and this is why I found this data. They found a bigger one, but I couldn't find information on that. So I'm not going to summarize too much. So I make that to be 0.158 to 3 decimal places. All right. So let's get our z-score. Oh, since we are doing this, and this is medical, right? And what do you want, 1, 5, or 10? What significance level should we do this hypothesis test on?
1.
Yeah, I think it's just safer to do a 1, right?
Mm-hmm.
Just for safety. So according to this, won't it be x bar, take away the mean divided by the standard error? And I've just made an oopsie here. It's a t-score, not a z-score, although it's a very similar formula. So what we're going to get here is 114.5, take away 115, divided by 0.158, and that is going to be a negative t-score. And it's negative 0.5 divided by 0.158. And I am looking at negative 3.164. So far, so good. Right. Now, I guess I might as well do it now because I forgot to do it earlier. won't the degrees of freedom here be 999? You know I won't have a 999 in the table that I'm going to look. So would I end up just using 1,000 anyway? Right. But technically it's 999. Now, if I was, oh, wait a minute, I'm going to use salt. So I can actually put in 999 now. I can actually use it. I forgot about salt. So I'm clicking on this right now and we'll put it in a few moments. But before I do, let's set up the null and the alternate hypothesis. The null hypothesis is that it stays the same, right? That drug had no real effect at all. And the second one is that it reduced it, right? And we have a significance level of 1%, and we have a t-score of negative 3.164, and we have degrees of freedom of 999, and we are going to get our p-value using salt, and the p-value is the probability that you get a t-score bigger or less than negative 3.164.
Less.
How can you tell just by looking at what's on this piece of paper here that it's a less? We've done these enough, so hopefully I'm just preaching to the choir here.
Because of the alternate hypothesis.
Correct. That says less, this says less. That says more, this says more. That says not equal to, we do that ugly two-sided thing, right? Now this is a less than, so okay. Keep an eye on anybody who comes in late, so you can tell me and I'll let them in because I got someone out last time. Now, am I in the right place? Correct, I'm not. Don't I need to change this to a t distribution? I don't know if you can see it, it's kind of faint.
We can't
Easy
see.
mistake.
We can't see your screen, so we
Oh,
can't see
well then that definitely makes it hard. I can see this. I don't know why you can't see the screen. Right, now I'll put it back to what it was like. That's what it looked like when I hit solve. And then I would say to you, be prepared for this question because you'll never guess it. Am I going to use this screen? No. Won't I have to change it to a t distribution? So that was the question I asked. I've just repeated it, right? So we've caught up with time. Do you know, I probably won't do this, but if I think about it, when I do the video, I'll edit out the first one and all you'll see is this one. I probably won't. Right, now, degrees of freedom, 999. Well, that's, whoa. It is what it is. On the question we've got here, isn't this a left tail test? I don't think this picture is going to help as much, but, you know, it's not necessary to know what the picture looks like. And I'm going to put in negative 3.164. Okay, and the answer that I'm looking at is 0.0008. Now that is a tiny p-value. You agree that is very, very small. Oops. As a percentage, it's 0.08%. So here comes, yes.
So that graph, that
Yes.
t-distribution, is that always how it looks? Just like this really skinny spike? Like, I don't understand.
That's scale. I think web assign's not great. If I shrink the scale and crunch the horizontal, it will look much more like a normal bell-shaped curve.
Because it just kind of seems pretty useless in that.
Yeah, for
form.
visual, yes. But you see this scale here, right? if I changed this scale, the horizontal scale, and you notice right now it's using hundreds. If I change that to -3 to 3, which is a much more natural scale, right? Maybe 5 to -5 because the t-distribution tends to be a little bit fatter. You would see a normal big flat curve just like everyone else. So yeah, the way that looks, that's not of any use to you. But if you change the scale, it would. So we got a really good p-value. Good because I know that's going to be significant, but we'll do the test anyway. And the test is our p-value less than our significance level alpha? And 0.08% is definitely less than 1%. It's actually definitely less than 0.1%. So it's really good. So our sentence would be something along the lines of there is enough evidence to reject. It's not. So if you got one of those 2 circle deals, you'd pick that one. But there's more to this. And so we can conclude that HA is true. That would be a much better sentence. Which means that haven't we proved that this anti-inflammatory drug has reduced the blood pressure of the people who received it? And so that's statistically significant. And the reason I chose this question, and I have not had that many to pick from, was because of this result. It's significant statistically. We have proved that this drug will reduce blood pressure. Right? And that is true. I'm not arguing that fact. But practically speaking, it's insignificant. Would you agree that if you took 115 and on average you reduced it down to what, 114.5, would you agree that that half point that on average people get is medically not a dangerous thing? Right. Half a point on your blood pressure, you get that if you eat a bag of nuts, don't you? You probably get that just by drinking a coffee or something, right? It's a kind of normal fluctuation. And the reason why I'm saying that it is practically, this is insignificant, is that sometimes people freak out when they hear a report about something being statistically significant, and then they say, oh, that must be important. Doesn't it depend on what the reduction is, whether that is a practical danger? I don't think, and actually in this particular story, the FDA were fine with it. They said, okay, we'll mention that to the doctors. It has been known to reduce blood pressure, but by an insignificant amount, like half a point. It's not going to cause serious damage. Now, if this was 115 and this was 100, right? Imagine that situation. It still would have been statistically significant, but now wouldn't it also be important as well, right? So there's a difference between proving something statistically is true and it being an important fact, right? I could prove that the difference between males in Texas, the average height of a Texan and the average height of somebody in Washington, DC, I could prove statistically that the Texans are 1/16 of an inch taller, right? Can you imagine I could do that? In the big scheme of things, is that really that important? Right? So if you get a drug and they say, oh yes, they've just found out that aspirin reduces your blood pressure. Yeah. Well, actually, I think aspirin's a bad analogy. This new weight loss pill reduces your blood pressure. Well, aren't a lot of people go and say, oh God, I can't take it? Well, what happens if the only thing it does is reduce your blood pressure by 0.5 point? Isn't it totally safe to take that particular drug? So just because you get this big news headline saying, danger, danger, this drug causes this side effect, look at how much that side effect is. Is it a big side effect? Like, oh, you lose 20 points on your blood pressure? That would worry me. Or is it like 0.2 of a unit, which is, not scared about that. And that's not always very clear. So I guess the bottom line is, when it is significant statistically, look at the two numbers and then say to yourself, no biggie. 115, 85, oh God, don't give anybody that drug, right? 115, 114.5, totally safe. Any questions about that one? I liked that question. It was a good piece of data. And last one then is I'm going to do a not equals to, and this is just a totally made up one, right? So for my totally made up one, you didn't know this because I have just made it up. Now the average number of soft drinks that an adult in America drinks in a week is 5 cans. I just made that story up, right? But pretend it's true, right? And a social scientist thinks that community college students drink more soft drinks than the typical population does. And so she goes and gets 200 random community college students, and she finds out, well, actually, she thinks that it's different than 5. Yeah, let's trace that. It's not 5, it's something else. And she goes and does it, and she finds out it's 6.1. And the standard deviation is 2. And she wants to know, is this enough evidence to prove that community college students drink a different amount of soft drinks than the typical population? So the null hypothesis is community college students also drink on average 5. And the alternate is that it's something different, right? It's not equal to 5. So we're going to do this is going to be our last statistical analysis. After that, I'll show you what some of the homework questions look like, and then we'll move on to our last section. Or not, depends on what time we've got. Okay, I need a significance level for this. Can I pick it this time? Yeah, I'll pick it. This is about drinking cans of Coke. I don't think I'm really worried about if I get it wrong. So can we do a 10%er on this? Now, that means I might get statistically significant result a little bit more often. Degrees of freedom, 199. Calculate my standard error. And I get 0.141. I'll find my t-score now, which is this guy, take away that guy, over the standard error. So 6.1, take away 5, divided by 0.141. 6.1, take away 5, divide that by 0.141. pretty. That's a pretty big t-score, isn't it? Wouldn't that be a phenomenally big z-score? T-score's got a little bit more wiggle room. So I'll get my p-value. Now, since I've decided that this is a two-tailed test, right? I'm just trying to prove that it's not equal, right? That one ends up being the funny looking one, right? Right, that's what the p-value looks like. It's a two-tailed test. So I'm now going to hopefully go over to WebAssign. And put this thing in the way. Hit both tails. Change this degrees of freedom to 199. Do you notice as the degrees of freedom change, the picture looks a little bit different each time? If I then put in, oh, it's got the two number thing going on for it. I'm going to do a negative 7.8 on this side. And I'm going to do a positive 7.8 on this side. And you see that little error 0 guy? You see that? Doesn't that mean that it's 0.8 zeros or something? So for all intents and purposes, it's 0%, which isn't a surprise. A t-score of 7.8 has came out. And we are now looking at our p-value, which is 0, or damn close to it. Right, we'll do our test now. Is our p-value less than significance level? Is 0% less than 10? Of course it is. And we can reject H now. I'm not going to do the whole sentence again. But see that sentence I used last time, the same one. Right, in practical purposes here now, haven't we got evidence to prove that community college students drink a different amount of soft drinks than the typical adult population? Right. So let's close this guy off, and I'm going to look now at some of the homework questions, see what they look like. Try and make them a little bit bigger. Okay, why can't I make you bigger? You should have a little plus minus up here. Wonder where it's gone. Play about with this for a second. There we go. Question 1 is one of those multiple choice questions. And you pick which ones you think are correct. I don't know if there's only one correct answer or more than one. I think there's only one in each case. So one of these two possible conclusions in hypothesis testing is to accept the null. One of the two possible conclusions in hypothesis testing is to accept the null hypothesis. No, you don't accept it. In hypothesis testing, the null hypothesis is assumed to be null. In hypothesis, the alternative is true, but not that. Oh, there, that's the one. When we do a hypothesis test, we actually only prove that the alternate is true. Right? If we get evidence, it only means HA is true, right? We're stating that as a fact. We don't actually say anything about what the null is. All we can say is not enough evidence to reject the null hypothesis, right? Or the null hypothesis is wrong and the alternate is true. So you can basically keep hitting buttons till you find which ones they are. And let's go to this one here. In this question here, you know that guy, you know that guy, you know that guy, and you know that guy. Can't you find a t-score? So won't you just do x bar take away mu divided by the standard error? And I have no idea what the right answer is, but can we pretend it's 1.23? And in this one, 2.4. Right? It's two calculations. So the question 4 and question 5 are just finding the t-score, right? So you're not going any further than just calculating that. And here we have a hypothesis test. I'll let you play with that one. Here's another one. Play about with that. I want this one. Okay, sample size 36. There's the mean. There's the standard error. If you put that together, you should be able to come up with a t-score and then a p-value. And you should be able to then decide based on a mean of 71. Okay. You want me to start question 8 because I'm just mumbling here and I'm not sure how much sense I'm making. Right. In question 8, you know that the mean is 71. I'm doing the females as an example. In the females, the data is a sample size of 36, an X bar is 76.7, and a standard deviation of 11.5. So what that would look like okay. I got my window in and can't see the bottom of it. There we go. Gotcha. Right. So I've basically taken all the information that they had in that table and it's here. And I'm going to take that information and we're going to make it into nothing yet. I'm fighting Windows again. If you could see what I'm doing right now, you'd be, oh God, what happened? Right, I get it. Go back to this guy. 36, that's the mean of women. That's the standard deviation. The null hypothesis is that it's 71. Based on this number, I would suggest that the alternate hypothesis is that it's going to be, it's going to be more than 71. I'd get my t-score. .7, take away 71. The standard error is this fella over that, which is 11.5 over that. It's about 1.91, maybe 92. Then I take this guy and I would go 76.7, take away 71, and I'd get that guy divided by 1.92. I'd get this guy. Right, at that point there, can you see I could then go into salt and I would find our p-value and then we could decide whether or not that would be statistically significant or not.
They're asking for a test statistic in that first part.
T-score.
That's a test statistic.
That's what I'm understanding to be test statistic. If it's not that statistic, but I'm pretty sure that one is, they might be asking for the p-value. I guess we'll find out. I could find out right now for us, actually. Oh, no, I can't. I'd have to go back out and in. I guess we'll find out. If it ain't the t-score, you'll try the p-value. If it isn't one of those two, you're going to ask me. The reason why I'm saying that is that the test statistic is a vague term. I've seen it used for z-scores, for instance. I would call that a test statistic. But I've also seen it used for x1 bar take away x2 bar. That would be a test statistic as well. Key hat is a test. Do you know what I'm getting at? There's, what one are you talking about? I think the question could have been clearer. So I'm assuming it's that. It could be. Now I'm thinking about it. Couldn't it just be the difference between these two? I don't know. That's a bad answer, but I don't know what they mean by test statistic in this case. I guess if you read their textbook, you'll see what they're calling a test statistic in this section. And that'll be the answer I would use. Apart from that, the rest of these questions are basically stories, and you set them up and you get your answer, and you are good to go. The only question that I can see that in my mind right now is going to cause you trouble is this guy here. The last question. A survey asked, oh, wait a minute, can you see question 12? Okay, let's see if I can make it bigger without losing anything. Okay. A survey asked students if they prefer to sit in the front, the middle, or the back of the class. And they also asked them their heights. The following data are the heights of 15 self-identified female students who said that they prefer to sit at the back. So that's what these numbers are. Female students who said they prefer to sit at the back. The mean age of the population is 65. They've just told me mu is 65 there. Okay. So I'm writing that down. H naught mu equals 65. You know, although you can't see it, that's what I just wrote down. Carry out a 5-step significance test. So I guess if you went through all the steps that I've done, there's probably at least 5 of them. So, right, just do hypothesis tests is how you should interpret that. Sit in the back of them. And we want to find out, is it higher? So isn't that mu greater than 65? Now, in this data, there are 15 students. So I'm now writing down n equals 15. And I'm going to return back to my piece of paper to kind of show you where this is going. The population is 65. The women that sit at the back, we think they might be bigger than 65. There's 15 in that sample. There are 2 numbers that you are normally given. In every other question, you are given. But in this question, you're not. How are we going to find the mean and standard deviation of that big list of red numbers that you can't see now? Type
it into the TI, the calculator.
Okay. Put into your calculator and do one variable summary. Can you remember that? You need reminding? Want to see it again? Okay, here it goes. Hit start, choice 1, edit. I'm just going to get rid of these guys. What you do is you type in all the students. I'm not going to do them all because it takes too long, but pretend these are the students, right? You type them all in. Once you've typed in all 15 of them, you hit start again, you move over to calc, and you choose one variable statistics. And in my case, you have to hit the blue button 1 so that you can tell them where the data is, and it's in line 1. And the mean in this case, by a sheer fluke, was a nice number, 63. Now, as you scroll down, you see that there's 2 guys that the 5.3 guy and the 4.7 guy. Do you see those two guys? Which one of those two is actually the standard deviation? Is it the 5.3 guy or the one underneath it? Can't hear you if you're saying something, Nikia.
I'm mostly talking to myself.
Oh, well then, what you were saying to yourself is, I think it's 5.3. Right, I'll put words in your mouth. The guy on the calculators that's called that, it's S with a little x, that's the standard deviation of the data. The guy that's next door to him that looks like that, that's sigma x. You're probably never going to use that one. That's actually the population standard deviation. So unless all your data is everybody in the universe, you're probably not going to use that number. Right? Because that would be if you knew every number in the population. So now that we've got this, can you imagine you can then build up your hypothesis test and go and do what you should have done? Actually, based on my numbers, this is not going to be very significant, but I'm sure if you use the real numbers, it would be. Now, we do have about 7 minutes left, and I want to start the next step. So, you can imagine what the next guy is going to be. The last thing that we're going to do hypothesis testing on, actually the last thing we're going to do entirely, is we're going to look at hypothesis testing for the difference in two means. Hypothesis testing, the difference in two means. So here's my story. Social scientist believes that, I think I should be calling the next one bar. Yes. Believes that males make more money than females of the same age. And so actually these numbers I got off the government, so they're probably pretty good. And so they looked at one group of people, 35 to 44. Do not ask me why the government split people up into that. I would have thought 30 to 39 would have been a more natural group, but whatever. 35 to 44 is how they do it, so that's how we're going to do it. And this is how, on average, what they make per week. 1,133 if you're a guy in that age group, 908 if you're a female. And we would like to assume then, or look at this and see whether or not there's statistical evidence to prove this. So I want you to pretend, because this is the made up part, that I got 100 random guys and that's what their average salary was. And I got 100 females. And there's no reason why the samples are the same size, I just picked them that way. And I would like to know, is this evidence to prove that on average males get paid more than females? So our null hypothesis and our alternate hypothesis are now going to be the difference between two populations. So you could say that the null hypothesis is that they're equal to each other, right? On average, women make the same as men. This was just a random sample that was a bit different. You've seen this before. Isn't this written as the difference is 0 instead? And in this story, I am looking for evidence that males make more money than females. So the alternate would be the mean of the male is bigger than the mean of the female. And of course, that's not how it's written. Would you agree that is pretty much the same kind of way you do P1 and P2 things? Remember when you were doing comparing two proportions, it was this way that you wrote the null and the alternate. So far, so good. Now, I want a significance level, and I'm going to pick 5% in the middle of the road. I've got all, well, I've not got all the data. So what I do have is that for the males, it was this, that the sample was that, and that the standard deviation was 15. And that for the females, it was 908. But these numbers are the only real numbers. The rest are made up. This is 100, and this is 20. So that's given information. I'm going to calculate now. That guy. You have seen this formula before. Does anybody remember what this guy is?
Standard deviation squared
Yes.
over n.
In this case, over N1 plus another one over N2, right? Essentially combining the two. We go on that? Do you remember it now that you've seen it? Right. I mean, there's lots of different formulas for standard error, but this is the one you use in this situation here. If I want to do a t-score, isn't that very like the P1 hat take away P2 hat formula that we did for proportions? In this particular story, we have 11.3, not 11.33, sorry, 1133, there we go. Take away 908, divided by a number I forgot to calculate. So let's just squeeze that in somewhere. So it's going to be the square root of 15 squared divided by 100 plus 20 squared divided by 100. And we got the answer 2.5. So this guy is 2.5. So we are looking at a t-score over 1133, take away 908, divided by 2.5, and we get a t-score of 90. Wow. That's a big t-score. You know, Z scores -3 to 3, T scores -5 to 5. Do you know what a t-score of 90 is going to look like? Isn't it going to be statistically significant? Now, I'm skipping a corner here, but I would go into SALT. I would do degrees of freedom. So I've got a t-score of 90. I have a degrees of freedom. We have to do that. Right. Made my life easy here. This one is 100, that one's 100. What's the degrees of freedom?
99.
99. Suppose one of them was 100 and the other was 200. What would the degrees of freedom be?
99.
Right, you take the little one and subtract one from it, right? So we got that, we've got that. So to calculate the p-value, I mean, there are not all overlap here. Isn't it very similar process, even though the stories are changing, the context a little bit different. It's going to get a t-score greater than 90. And can you trust me that the answer ends up being 0%? And then we do our test, and it's not a surprise. Is the p-value less than significance? Is 0 less than 5%? And yes, it is. So this government data, although I made up my sample sizes, I'm sure it would be realistic. We have got evidence that males get paid more than females. And that is a known fact. I think nobody argues, well, very few people would argue that that's not the case. What's kind of interesting is the explanation of why that's true is all over the place. One explanation of why that is true is basically sexist. People pay women less money than men because they can, or because they choose to. It's been quite a long time in America that they've had laws that forbid that. You know, if two people are doing the exact same job in the exact same company, if one of them's getting paid less than the other because she's a female, doesn't she sue that company now? Good. I believe that's good. Now, they can get around it. They can say that the guy's a manager and she's not. That's why he gets paid 20% more. I guess they could try that. But you could only do that so many times before it would probably not work in a court case. Because you take them to, a particular type of court and it gets tried on. So what are the reasons? Why are women paid less than men on average? Because it is true. Or maybe it is true. Maybe just businesses have found a way of paying women less.
It just depends on what you're talking about. If you're talking about a woman in the same exact profession or just women overall.
We're talking women overall. You're on the right track, Nikia.
Yeah, because women tend to take lower paying jobs, such as teachers and things like that.
Yeah. When you look into the data, one of the reasons, not the only reason, but one of the reasons is this is an overall thing. It's not women doctors get paid less than men doctors, although that might be true, right? If you look at within the same profession, the differences, if there are any, are not normally that bad, right? But if you look at overall pictures, women tend to do jobs that get paid less, not because they're less important, but they get paid less, right? I think of something. Oh God, brain's gone. Guys like doing jobs that are dangerous, and dangerous jobs get paid more, right? I'm sure a lumberjack gets paid quite a lot of money, but there are not that many female lumberjacks. Women like kids. Nursery teachers is a great profession, but you're probably not going to get paid the same amount of money as somebody who teaches at university, right? Certain jobs, women, for historical reasons or maybe just emotional reasons, they like the job, do it, right? How many male nursery teachers do you know?